Hello, community. So great that you are back. Let's talk about two paths to AI. And let's be more specific, to a trustworthy AI system. Because we still have the problem of the last mile of trust in our AI models. Let me give you an example. Just 16 hours ago, I had here this beautiful publication here by Tom's Hardware. And they tell us here, somebody applied here an AI agent here live in a productive environment in a company, and AI just deleted here records here from 1,200 executives, more than 1,200 companies, just wiped out by the AI. Yeah, it just happened. And you might say, who would do this? Who would say, I will put an AI system into a real productive system? No? Of course, this can happen. But, this last mile of trust is so important because, we're saying, hey, great, LLM have a remarkable capacity of understanding everything, immense excitement. But the moment we go here to a real operational system, like in medicine or in production, this last mile of trust becomes immense important. And currently, we all feel this crisis of trust. Because an AI is kind of a black box, no? It might hallucinate. And in a causal conversation, if you just talk to an AI, hey, this is nice, maybe it's a curiosity. But if you have here a real industrial application, for example, to identify here a drug, the side effect of a drug, and AI makes a mistake, this can be a catastrophic failure. So, there's a solution. No, we have RAG. No, the principle is simple. Prevent the LLM from making things up. So we have to ground it in external, proven, real data, in facts. And a standard RAG relies here on a semantic similarity, a cosine similarity, and we use this having here transformation and mapping to vector embeddings in a new mathematical vector space, let's say 1,000 dimensions or 15,000 dimensions. And great, standard RAG reduces here the hallucination, but it does not eliminate imprecision. So if we really have some high-stake factual verification, we need to close this last mile gap between the probabilistic similarity of a cosine similarity and the real deterministic truth. How we do this? Well, we need the LLM's conversational interface, but with the logical certainty of a database lookup. So we have now a new axiom of verifiable retrieval. And for a high-fidelity factual verification, the probabilistic ambiguity of semantic similarity retrieval can be eliminated, simply eliminated by restructuring the knowledge source now as a formal graph and translate your user query into a deterministic, symbolic query executed now against this graph. And you see what's happening? We completely reframe the LLM's primary role as a generator of answer to a presenter of some verified external facts. So, an LLM should not be asked to reason, to infer, or to synthesize from retrieved text. LLM should be used to orchestrate here a formal query and then clearly communicates its results. Let's do a simple experiment. In physics, we always do this. Computer science is part of physics. So, somebody did it already for us. Great. So we have here by Kwaai, here from US, Center of Space, Biomedicine, University of Pittsburgh, the Broad Institute of MIT and Harvard, and some university here in Paraguay. Hello, wow, nice to see you. A new study, RAG-based architectures for drug side effect retrievals in LLMs. And they really looked at it. And just give you here, Broad Institute, was not familiar with it. It is here a partner of MIT and with Harvard University and the 5 Harvard teaching hospitals. And yes, I still use Wikipedia. So, what they did, it was easy, no? You need a database. They have here a CIDR 4.1 database. Great. It's a primary knowledge source. It's about everything that we know here about some, whatever you call it, some anatomical, therapeutical, some chemical classification, side effects here by some, yes, great. So what we have a data set of 140,000 associations. That's all we need to know. And then, you know what we do? For this demonstration, we reduced the complexity to only 19,520 drug side effect pairs. And then we have a data format. And let's go for it. No? You know, with a classic RAG, we have here a text splitter with chunks, and then we have some embeddings. And they decided to go with here mathematical vector space of 1536 dimensions. And then you make a mapping here to a vector database. They go here with a commercial one that you have to pay for, and great. So we'd ask, so what is the result? What is the performance? Now, the standalone performance of only Llama 3.8b without anything, we have an accuracy of 0.5 and F1 score of 0.1 and a sensitivity of 0.09. So this is in no way acceptable in any way or form. So never ever go here with a standard off-the-shelf LLM. So with RAG and the data format A that we extracted now, and we have here some beautiful RAG now. So the accuracy goes up to 88% and the sensitivity goes up to 77%. But in medicine, 77% is not enough. This is not that you can say, I can apply this here in a real world test case, no? So RAG is not good enough. And yes, they went through everything, AWS Lambda and Amazon Bedrock and everything beautiful, and they paid for a Pinecone. And you say, yeah, they spent here all their money, and yeah, because simply the methodology is here not good enough. And there is a solution to this. And you know the solution. And it is an easy solution. Because as a subscriber of my channel, you know that we talked about this now for more than a year. Graph RAG, speculative RAG, here graph neural network on graph RAG for the reasoning graph RAG versus in-context learning of graph RAG evolved to path RAG to relational reasoning path. And we go beyond graph RAG. But no, here today we stick with graph RAG. So it's easy, no? We have our database, we build our graph, and then we have a graph database. Let's go with Neo4j as the authors did. So what we have the drugs, and all the side effects constitute now different nodes in our graph, and the relationship between the nodes are encoded here as edges. It's standard. And specifically, they are now labeled here the edge attribute as it may cause a side effect. And this is now in the Neo4j database, and we can query this with Cypher. And if you're not familiar, Cypher here is easy to learn. It's a declarative learning language here. It is similar to SQL, but now optimized simply for a graph object. So if you want to see this for the graph RAG framework here, we have Cypher and we have a simple query. So you see we are not operating with cosine similarities in a constructed mathematical space where we measure here maybe an insufficient quantity of an epsilon environment that is close by to another class of vector representation. We have here pure code. So not probabilistic, but deterministic code. And we go here to everything, Neo4j and AWS Lambda and Amazon Bedrock, and you pay for everything, and great. So you have here the complete workflow. And we go with a Llama 3.8b. Now graph RAG is now nearly perfect. Look at this. Accuracy, 0.999, F1, 0.999, precision sensitivity. Absolutely fascinating. And you might just, if you are interested, say, why? Why is this happening? Well, we went away here from a probabilistic system to a deterministic system, no? Graph RAG, by representing here the drug side effect association here as a graph, we have now a highly precise relationship-driven query that reduces here the ambiguity and enhances here the retrieval accuracy because we're working now with a graph database. Let me give you a simple example. Yeah? Let's say we have a query, hey, can this element here cause something? In the standard RAG process, if we work here still in a probabilistic view, now is search a vector database here for the text chunk here of the query. No? And it might retrieve here from the epsilon environment here in a mathematical vector space here some chunks. Chunk A is here. Yeah, this is an anticoagulant used to prevent blood clots. Or B, common side effect of anticoagulants include. But you see, there's no direct relation between our two objects in the query. So the LLM must now read the chunk A and the chunk B and infer, not to say reason now internally, that because this element now is an anticoagulant and anticoagulant causes a specific effect, then it is a logical deduction, or maybe not, that this will cause exactly this effect. So this inference step is where the ambiguity and the errors can occur, and they do occur, because this reasoning is for an A to B, not on the level of a complexity for medical analysis. So you see, this was the standard RAG, and this is why vector databases and RAG, we don't use them anymore. And graph RAG is now, if you look at it, a deterministic process, no? Because we have two entities, two entity recognition here. We have the drug and the side effect, and then we just construct here a sci-fi query for a graph database. We execute the query, and it returns here, if it finds a direct edge connecting here, node and another node that we defined here, the drug and the side effect, it returns the edge object. So this system reports yes, because the link was found. You see, the beauty is there's no inference, there's no reasoning, there's nothing. It is just a query. Hey, yeah, no. So the result is a direct logical lookup. And the near-perfect accuracies reported is a direct consequence of the design of graph RAG. Now, careful. Don't interpret too much into this, because what we did, or what the authors showed us, is an extraordinary accuracy for the defined task. But look at the task, it is verifying the existing of a single directed relationship, or if you in graph, a one-hop query. It does not answer in its current form, or published here by the group of authors, multi-hop questions, like, hey, a little bit more complex. What are the common side effects of the drug that they use to treat here the conditions that are caused by hypertension? It is not doing this. It is just going for a single direct edge, and this is it. And it is replacing a probabilistic semantic search, like RAG, with a deterministic symbolic querying, and this leads you to the leap in accuracy. But you know what we learned from this? That the structure of the knowledge source, now being not a database but a graph database, is as important as the content of the knowledge source. Now let's have a look at the results. And remember, this is only for one hop complexity, no? Graph RAG, beautiful. But you know what? They did here an experiment with RAG that we showed is not working in another data format, and this RAG that we already said, hey, it's not working, has now an accuracy of 0.998, accuracy of 0.999, and a sensitivity of 0.999, and if you compare this with graph RAG, sensitivity 0.999. And you see, what? What happened? Well, it is easy. If you understand exactly what is happening and the methodology, you say, yes, I expected this. Let's have a closer look. So factual retrieval, the structure of the knowledge source, is just as important as the content. So this means if we had a look at a classical RAG, the data format A, where we have everything here in a paragraph or even a long sentence, with multiple sub-sentences, and my goodness, no? Like the drug aspirin causes the following side effect, A, B, C, D, E, F, G, and then easy, no? Then we embed everything together. We mix everything together. We concatenate, we calculate here some whatever probabilities or maybe some average, and we build here a mixture, a slash here of elements here of tokens that we squeeze together, and then we create a vector. Now this vector embedding here for this aspirin chunk, however you chunk it up, then represents here an average, meaning all the listed side effects here are now squeezed together. So this specific signal, if we're looking here for a specific technical term or medical term, this term might now semantically be diluted by all the other terms here in this specific sequence. Now, if we have another data format, and you are gonna love how easy it is, look at this, what they did. They now said, if we understand that this complexity is too high, so we make it easy, no? We have now for the drug aspirin may cause this as a side effect. And then we have another sentence. The drug aspirin may cause B as a side effect. And then the drug aspirin may cause C as a side effect. So we now have a complete different representation of the identical content, but now we go for a sentence representation that is extreme low complexity. Whatever we do, it's always the same rule book, no? Reduce the complexity, create multiple simpler complexities, and then continue to calculate those simpler complexities. So the vector that is now created has here the drug aspirin and a specific effect as a side effect. Nothing else, no delusion. Absolutely precise. So the vector is now compared against the query vector, and suddenly we have a beautiful cosine similarity that is real close. Why? Because the query vector is now extremely similar to the vector for what we defined. So you see the retrieval is no longer a real fuzzy search here in a paragraph of text, but it is rather a precise match to a factual statement. So easy. Now, by making here each document an atomic fact, and it's not said that you can do this in general, but if you can do this, if you can reduce the complexity down to a level 1 complexity, the authors here showed us essentially they turned their vector database into a high-performance key-value store only, where the query is the key and the factual sentence is the value. So fascinating that they had this idea to reduce the complexity totally. But you know where it fails? On higher complexities, of course. But just think about it. It is a near deterministic process what we achieved here, and the performance of RAG in the version B is almost as good as GraphRag. So if you understand it, you can play around and get optimization that even RAG B is almost as good as a GraphRag. But you remember, this is still a search algorithm, and GraphRag is still a logical query algorithm. So careful. Yes, you can trick the system, but you have to have a deep understanding of what you are doing. So nice, this publication. Yeah, the author showed us that you can make a standard RAG if you know exactly what you're doing and you have a very particular use case. Standard RAG almost as good as GraphRag if you structure here your source documents as individual atomic facts. This can bring you a lot of improvement in speed, reduce the cost, and but careful, this is only for singular cases with a low complexity. Okay, this was the warm-up, this was the introduction. You might say, hey, I know everything, so what is new? Okay, let's start the video. Now you know that we already talked here about a singularity that is here showing us, hey, almost as good as human. And then in the next one, I talked about superintelligence here by Princeton University, already discovered. And Meta says, what? I just built a superintelligence team. I'm so sorry, Meta. But it's already solved by Princeton University. So, but think about it. Think about the methodology and the algorithms that they applied. And they are now on the different side of the spectrum. No? Let's have a look at this. Let's look at my last video, Princeton Bottom-Up Superintelligence. And I call it the internal is cool. No? It's kind of a philosophy because it says that the true expertise must be embodied in the intelligence. Knowledge and reasoning cannot be external. No? They must be woven into the very fabric of the model parameters, whatever you go, let's say a typical transformer, through some intensive training. And I showed you here in the superintelligence that we have supervised fine-tuning, which is nothing else than a specific form of the after version of a RL algorithm. So the goal here with Princeton was to create here a virtuoso, an agent that reasons here from internalized first logical principle. It is an absolute expert, a very narrow expert who has seen so many cases that the reasoning process becomes, quotation mark, second nature. Now, the GraphRag paper of today with Broad Institute and Kwaai, they have now a different idea. The philosophy is of complete externalization. So we have here an approach of an augmented verification. If you think about RAG, the retriever augmented generation. It tells us here the LLM should not be the source of the truth. The LLM should be just an intelligent switch, an interface to an external, auditable, and dynamic, updatable source of truth. Well, think about it. This is not really true, but more about this later. But it's okay. This is the statement they want to see this. And the goal is to create here an oracle, a system that provides perfectly grounded answer by querying here a verifiable repo. And this might be your database, or this might be a news database. This might be a database that goes to CNN, or a database that belongs here to Fox Entertainment. You see, you just transfer the question of truth here to another object, not the LLM, but to a database or a graph database or any other structure. Let's compare this to a human example. You see, this case here is the brilliant young doctor who doesn't rely on his memory because he's never done anything in the hospital, but he can flawlessly use here his ChatGPT to use the most up-to-date medical database and inform every decision, perfect in SQL programming. He knows everything on a theoretical level, but he has no experience by himself. So he knows where to look for in the library, but he has not experienced anything. So what do you want? What do you prefer for a system? A graph rag system? Show it here even side by side. Yeah? So this bottom-up is Superintelligence by Princeton. In my last video, the main idea was to internalize the reasoning process. And the model itself becomes the reasoning engine. GraphRag and the application here sees it different. Yeah? This is to externalize the fact retrieval. The model uses here a factual engine as to truth. However, the bottom-up superintelligence here by Princeton had a beautiful feature, multi-hop compositional reasoning. It's explicitly designed to solve higher complexity problems like A to B to C. And I showed you in my last video, we can go up 7 steps here in the complexity aggregation. GraphRag, as shown today in this paper, is a single hop direct edge association. It is explicitly designed for one task and one task only. I have here a drug and I want to have its side effect. Stop. That's it. So I have a direct fact that links A to B. This has a defined level of complexity, a low level of complexity. Now, to make it even clearer, the Princeton paper on superintelligence teaches us how to build an AI that can think like a real human doctor, an experienced doctor, learning the very process of differential diagnosis and logical deduction. The GraphRag paper of today teaches us how to build an AI that has perfect access to a doctor's entire internet library and can cross-reference every little fact instantly. Of course, you would say, hey, wait a minute, the ideal system would be, of course, if we could combine both. So you might ask, can we fuse here an internalized compositional reasoning engine with a dynamic external verification system to create here a brand new model, the very next generation of AI that is both a deep reasoner and a reliable fact checker? This hybrid model now represents the next frontier in AI, in model development. And I think this will be a crucial step toward creating an AI that we can truly trust with our most critical task. But we have to get it right, and we have to understand if we have now a combination of internalized compositional reasoning with externalized verification system, that there are some inherent challenges, but I think this would be the topic of a next video. So if you like this kind of videos, hey, why not subscribe? And I see you in my next one.